Hi everyone! Hi friends! Welcome to this new video. 2 weeks ago I made a love lesson about an introduction to QFT. What is QFT? Why we have QFT and many other questions about this beautiful branch of the physics, quantum field theory, QFT. Today is the first lesson in this course and we're going to talk about quantum mechanics, QM. Okay, and so there are two lessons. Introductive lessons about into this word QFT. I love it and I'll try to make you love it. And so there are two lessons. One of them about quantum mechanics. So this lesson. Okay, quantum mechanics. In this lesson, what about this lesson? We're going to talk about bracket notation. Bracket notation. Okay. um. Oh, I forget that. Bracket notation. Then. Okay. Yeah. Schrödinger. Schrödinger. And Heisenberg. Heisenberg picture and wave function and harmonic oscillator. The most is a quantum system, okay? Because I have a classical dynamics and through a method called canonical quantization, there is a corresponding quantum system, okay? For each classical dynamics, there is a corresponding quantum system, and this is very important. And this is the basis of QFT, okay? Because QFT tries to find these systems, okay? Wave function and this system through mathematical concept called the field. Wave function and so harmonic oscillator. Then this, I'll make a lesson about special relativity. A moment please, okay. So a lesson about special relativity. Special relativity and a bit about groups theory. Special relativity and groups theory. I want to say a thing. These two lessons can be considered formal lessons about quantum mechanics and special relativity. In my channel, I'm doing a course about quantum mechanics, and that is a formal course, a rigorous course about quantum mechanics. But these two lessons are a brief introduction to QFT. But these two lessons don't help you to understand morely quantum mechanics and special relativity, okay? But if you are interested by quantum mechanics, you can watch my videos about quantum mechanics, rigorous videos, okay? This is a brief lesson about quantum mechanics, just to introduce QFT. So in lesson about special relativity and groups theory, we're going to see Lorentz transformation, Lagrangian, and Hamiltonian formulas In my channel, I made a course about Lagrangian and Hamiltonian formalism. But these two formalism, I talked about these two formalism for a classical system, okay, for a corp, for a body. While in this lesson, in the next lesson, we're going to see these two topics in another way. Lagrangian and Hamiltonian formalism for a field, okay, not for a body. Lagrangian and Hamiltonian formalism. Formalism. Then Lorentz group, and Poincare group. Perfect. Okay, so these are the two lessons to introduce QFT. From the third lesson, we are going to talk about Klein-Gordon equation, interaction theory, and so on. But what is QFT, and why do we need a QFT? So a quantum field theory. So QFT is a way to talk about quantum field theory. And what is? So since the time of the Greeks, they try they fought they looked for a way to describe the interaction between bodies, okay, a mathematical way, a physical way to describe this interaction. So since the time of the Greeks, they are interested by finding a mathematical way to describe this interaction, this relationship, okay? And then in 1600, Newton began started talking about field. Gravity. Newton started talking about gravity. This particle force. What does force mean? Force is a simple word. This word can be explained by Greeks too, but in modern physics, yeah, isn't so, because the force is the most difficult word in the physics. So the physicist looked for a way to describe it, this interaction, and after Newton age, so when Newton thought about force about gravity like a force, Einstein arrived and started thinking about gravity like a field. Okay. So this mathematical concept called field is a bit difficult like topic in mathematics because is a function, is a vectorial function, and we can define this topic, but we aren't interested by this. Okay. We aren't interested in this. But for example, is a vectorial function f of this type. Okay, for example, so I take a vector, a 3 vector, and I receive a 3 vector again. So with the same number of components. So f r and r and okay, perfect. Now this is a field, a general definition of a field. But how to introduce this concept in physics? How to do? So we wanna describe the interaction between bodies, okay? And so physicists introduced this concept called field. For example, we have two bodies, okay? Two particles, for example, particle A and particle B. So, for example, Earth and the Sun. Why does Earth turn around the Sun? Why? There is an interaction between Earth and Sun. Okay, there is an interaction, but this interaction we can't watch, we can't observe this interaction. And so, if we can't observe this, we can't describe. But it isn't right, this isn't right, this isn't right. And because there is something between these two bodies, this something is the field. More carefully, is the moving of the field. Because imagine that there is a paper between these two bodies. A paper, okay? So, a square paper, and this particle, for example, it's a charge, mm, excite this paper, okay, make it excite, and so this paper start moving and pushes the second particle, okay, and the second particle start moving. So the moving of this paper make second particle excite, and this is the work of the field of a field. So this moving of this paper pushes the second particle, and so there is a relationship between these two particles. For example, for here to the sun happen the same thing. The same thing happens for the case of Earth and Sun, the gravitational field. And we had a genius in that period, Einstein. Albert Einstein found a way to describe gravitational field with the famous equation G mu well, 2a pi g on c to 4 t mu nu. This equation, called Einstein field equation, describes how the gravitational field moves in the space-time and um, in the space-time and but it considers the interaction with matter too, okay? Because considering the matter is a bit more difficult, okay, than not considering the matter. For example, in electromagnetism, it's very difficult considering the matter in the Maxwell equation, okay? So this example for field is in a classical relativistic field theory, not quantum, and a relativistic theory. Now, here I have to add relativistic because there exists some some theories that aren't relativistic, okay? So why relativistic? Because this paper is over the space-time, the flat space-time, and this flat space-time is called the Minkowski space-time. Now, in the case of gravitational field, Einstein found out that the paper isn't over the space-time. The paper is the space-time. And so if this paper start moving, space-time start moving. But with moving, I wanna say the level of exciting of the paper, okay, the perturbation of the paper. So not paper moves, okay, moves it into space, but paper paper is excited, okay, and so the space-time is exciting, and so the space-time start curving, okay, so we don't have a space-time as flat space-time but a curved space-time, okay. This is the big idea of Einstein. So this is a classical field theory. For a quantum field theory, it's a bit difficult. A relativistic classical field theory. For a relativistic quantum field theory, it's a bit difficult. Okay, it's a bit difficult, but we will study it. Okay, but now we want to talk about quantum mechanics. So let's start. So. Um, we start with bracket notation. So bracket notation. So we have Hilbert space. What is Hilbert space? It's a vectorial space. Okay, so it's a vectorial space, and it has particular properties, but I don't talk about it. Anyway, it's a vectorial space, and so this Hilbert space is a complex space too, but his elements are a vector, phi, for example, psi, and so on. Where this notation, in this way, is a particular way to write a vector, okay? And this vector is called this way to write a vector. Okay, we obtain so a vector writing this way, and it's called ket vector, or ket. Okay. Now we have a basis for this space, and this basis is ek. Okay, 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 and so we can write the ket vector psi like sum of k of psi k for ek. This is the new way to write the psi. What does it mean? For example, in a real space with 3 dimensions, R3, we have 3 vector bases. Okay, I. Okay. These are the 3 vectors that make the basis of the space. Thanks to this vector, we have this. Thanks to those 3 vectors, we can write any other vector. So, for example, 3, 5, 6 is equal to 3 for I plus 5. Okay, and where this 3 is called components of the vector. Okay, so 3, 5, and 6. So in this expression, we have pk that is the component of the vector, and and ek that are the components of the basis. Okay, perfect. This way is very smart, elegant. Okay, so this is a cat vector. Now, for example, we have a linear function, and her action is over psi. For example, alpha for c1 psi1 plus c2 psi2. Okay, this function is equal to c1 half 1 c1 plus c2 half 2 c2. Perfect. Now we can write alpha in this way. Okay, this called this is called bra vector. Bra vector. A bra vector. Perfect. Or bra. Okay. Now the action of alpha over psi is equal to alpha for psi, and this is equal to alpha. Oh, sorry, I forgot. Alpha. How to explain this vector? Alpha is equal to sum of n of half n for what? Not this, but another basis, not for h, but another space that is the space where alpha lives. This space is called the space is called the dual space of H. Okay, the dual space. It's a famous definition in functional analysis, for example. Anyway, or in linear algebra, in tensor calculus, and so on. Anyway, this vector so is equal to this, and so I can write so kn of psi k for alpha and for epsilon k ek, where epsilon k is a basis for the dual space, okay, of H. Now, for the orthonormal condition of a basis, such that epsilon k for ek is equal to delta of this is epsilon n is equal to n k, where this delta is the Kronecker delta. Okay, if n is equal to k, we have 1, and if n is different from k, we have 0. So if n is equal to k, this is equal to 1, and so this is equal to sum of n, for example, Cn of n. Okay, or we can write, because it's better, f and Cn, because we have yes, half 1, half 2 for psi2, psi1, okay, and so half n for Cn. Perfect. Okay, okay. Now, so this is a kit vector. This is a bra vector. If we put together these two vectors, bra and cat, we obtain this, and this is a bracket. A bracket isn't a vector because I'm multiplicating between them two vectors, and this vector can be explained like a row vector, while this psi is a column vector. Okay, And so a row vector for a column vector, we obtain a matrix, so a tensor. And so this is a matrix or a tensor, we can say. And so this is called bracket. Bracket in English, so in Italian, um, the meaning is parentesi. So a bracket in English, there exists this word, and in Italian too, parentesi. So this is a bracket, bra plus cat, bracket. Perfect, perfect. Okay, now, for example, the action of a cat over another cat. Okay, what is? Oh, sorry, for example, we have phi psi thesis. Phi for psi, where phi is the corresponding element of phi in H, but this bra phi is in dual space of H, okay? So it's the corresponding element in dual space of phi in a normal space H. And so I don't show these, but this phi is equal to the conjugate of phi cat. Okay, perfect. And so in this way we have the expression of these two vectors. So sum over n and m, or m and n, of phi conjugate n for psi m for n. And so in this way we have, if n is equal to m, we have 1 for phi conjugate n for psi m. So this. Okay? Now, if phi is equal to psi, we have a particular thing, and but in this way, remember this thing. Thanks tensorial calculus too, because when phi is equal to psi, we have the same vector, but one of these is column vector, and another is a row vector. So we obtain a scalar, okay, not a tensor in this case. And so we have a scalar, and this scalar is the square of the norm. Perfect. So the norm of psi is equal to square root of psi for psi, okay? And so this is sum of n. This psi for psi is equal to this. Yeah, okay. And this is the square of the norm. So we do the square root and we obtain the normal vector, and the normal vector psi is equal to square root of psi for psi. Okay, now a relationship between the vector and the basis of this vector and the component of this vector. We have an orthonormal basis for the space. So for example, we have psi, the cat psi is equal to sum of k of ck for ek. Okay, and if we had ek in this way, we obtain this, and this is equal to 1, okay? But attention, because this is equal to 1, okay? But now we have that ek psi is equal to psi queso, okay? Perfect. So in fact we have, we have sum of key A cap psi for A key and is equal to psi, of course. Okay? Okay. Well, all right. Now, we have to talk about. Oh, okay. This is very interesting. So this is an operator. Um, Sum of this, and this is the identity operator I. Okay, in Hilbert space. Now we can talk about the axioms of quantum mechanics. Perfect. The axioms of quantum mechanics, because in this lesson, where do you see the quantum mechanics? This is a mathematics. This is mathematics. In fact, this is a way introduced by Dirac to introduce in quantum mechanics mathematics, because the physics without mathematics is nothing. And so quantum mechanics is very quantum mechanics like playing hide and seek, and we have to look for her, and so quantum mechanics likes playing hide and seek. We must look for her and find her, and the best way to find her is build a mathematical theory behind the physical theory, okay? And Dirac found this way to describe mathematically quantum mechanics with bracket notation or Dirac notation. Okay, and so now apply this to quantum mechanics to introduce the axioms of canonical quantization. Okay. So this is the second topic in this lesson. And so canonical quantization. Okay. So we have four axioms. The first axiom is first. We have there exists a Hilbert space H. There exists a space H. Okay. Oh, I wanna say a thing. Given an isolated system, classical dynamics system, such as an harmonic oscillator, the most easy system, for example, we can construct a corresponding quantum mechanics. This is the work of canonical quantization. So building a corresponding quantum system. And there exists a Hilbert space H for a quantum system, okay? So for a quantum system, we can move in space Hilbert. Okay, perfect. And the state of the system is required to be described a vector psi, or and state of the system is described by a vector psi in the space. Okay. The state psi and for example psi and C for psi, where C is a constant, is are the same state. Are the same state. Okay. Now, so if we build a quantum theory for a system, we have to move in Hilbert space, and a state of the system is described by this vector psi in H, a ket vector. Okay? Perfect. This is the first axiom. The second axiom is okay, a physical quantity, for example, energy, so or angular momentum, a physical quantity A. So where does what does A become in a quantum system? So in classical mechanics, is replaced by a Hermitian operator. Yes, replaced by Hermitian. What does it mean? Hermitian operator. A is equal to this. Okay? Perfect. Okay, so this physical quantity A in a classical system becomes a Hermitian operator, okay, A, called observable too. Observable. This is very important. And the result obtained by a measuration of A is the Ng value of A, and the set of Ng values of A can be discrete or continuous. 3. The Poisson bracket. The Poisson bracket. Poisson bracket in a classical system, for example, A, B, is equal to a commutator A, B on high H. Okay? Okay, perfect. For example, we have Qi, Qj is equal to pi I, pi j is equal to 0. Where Q and pi are two operators, the position operator and the momenta conjugate operator, okay? Perfect. And Qi for pi j is equal to I delta between I and j. For h, of course, for h equal to 1. Okay. And the Hamilton equation for motion becomes with an I. Okay, perfect. And then For example, we have I because we have I dimension and I here, okay? These are the Hamilton equation of motion. And so, for a general operator, we have the Heisenberg equation of motion. This equation. Okay, where H is the Hamiltonian operator. Perfect. Now the fourth axiom. The fourth axiom. Oh, remember this equation because it's very important. This is the quantum version of a Hamilton equation. Okay, so this is the Heisenberg equation of motion. Perfect. Okay. Okay, fourth axiom. Let C be a vector in hyperspace, of course, an arbitrary state. Suppose one prepares many systems, okay? Suppose you prepare many systems, okay? Many systems, yeah, right, and each of which, okay, which is in the state is is in the state psi, okay? You prepare the systems and each of which is in this state. And then observation of a quantity, so an operator, then an observation of a in the system at time t. This observation yields random results, okay? The expectation, I don't write, the expectation value of A of the result is given by A. T is equal to psi for A of T for psi on psi for psi. I forgot a thing. When a vector is called normalist, a vector is normalist when the norm is equal to 1. Okay. Okay. Now, what does this axiom mean? Okay. So, we have what? The operator A of t, his action of a state n gives a engine value a n for n. Okay, so this operator have this discrete set of engine values, and we have this. Okay, so the state is normalist. Now we are in the state psi, and psi is equal to sum of n of psi with n for n. Okay, perfect. And so psi n is equal to n for psi. Okay. Now we have psi for psi is equal to 1, and so psi for a of t psi is equal to sum of n m of what? Psi conjugate n for psi m, okay, for n for a of t m, and this, if n is equal to m, we have 1, and so we have sum of n of what? Of a n, okay, a n for psi n square. This is the result. Perfect. Where this psi n square is equal to n for psi square, and this n for psi is called probability t amplitude. Okay, this is the probability amplitude, or the weight of the measuration. We can have the case where the psi has a continuous spectrum, a continuous set of eigenvalue. In this case, we have psi is equal to integral into a for psi of a for a, okay, where we are integrating over the set of the possible values of a, okay. Now the normalization condition for the basis is this: a prime for a is equal to another delta, not the Kronecker delta, but the Dirac delta, okay, delta of a prime minus a. Okay, this is the Dirac function delta, the Dirac delta function, and psi of a is equal to this. Okay. Now the normalization condition, psi for psi is equal to 1. So 1 is equal to psi for psi, and is equal to integral of, we have two integral, okay? Because two integrals, because this is two vectors get in a Hilbert space with a basis, and another vector, bra vector, in a dual Hilbert space with another basis. So we have two set of two possible values, okay? Perfect. So d a prime in the a, okay, it's the same, but we can write a prime for psi conjugate of a for psi a prime, okay, for psi prime for a prime, and this is equal to integral for integral into a of psi a square, and this is the probability amplitude, okay, to find the result in an interval a plus ta. Okay, this is the normalization condition, and so in this way, psi for a of t for psi is equal to integral in the a of psi of a square for a. Okay, perfect. Now we can talk about Heisenberg and Schrödinger pictures, the third topic in this lesson. So we have now so Heisenberg and Schrödinger pictures. Okay, Heisenberg and Schrödinger pictures. So we have the Heisenberg equation of motion, this, and the solution of this equation is a of t, because the operator depends by time. Okay, this is the very important thing. A of t, the solution of this equation, is a of t is equal to e to a I h t for a0 for a e to minus I h t. Okay, we have this equation. Now we have this equation, and where the operator u of t equal to e, this operator is in the basis of Heisenberg picture, because Heisenberg picture describe the operator like dependent by time. Okay, the Heisenberg equation, while the state psi doesn't depend by time. Okay, and this is the Heisenberg picture. Now we can find the Schrödinger equation, the Schrödinger picture, while in this way. A of t, so the expectation value in the time t is equal to psi for EHT for A0 or A. So the solution of the equation, and this is equal to psi, the operator E to HT that action on psi for A0 for the operator U that action of psi cat this time. So this can be called psi of t cat. So this is a vector. This is a vector. This is a state vector. This is a state dependent by time. And this is the conjugate, so psi of t cat. And then we have the operator. The operator this time doesn't depend by time. So we have this psi of t for A for psi of t. This is the Schrödinger picture. So in Schrödinger picture, we have that the operator doesn't depend by time, but the states depend by time. Okay. Now we can find in this way the Schrödinger equation of motion, uh, because psi of t, so this is Heisenberg equation for Heisenberg picture, and for Schrödinger equation we have that psi of t. So what could Schrödinger equation say? Okay, so start with by starting with the Heisenberg picture, the Heisenberg equation. What could Heisenberg equation say? Say as the variation with respect to t of the operator, so the variation of the expectation value. And so now we want to find the variation of the expectation value with respect to time, but in this case we have in the Schrödinger picture, so we want to find the variation with respect to time of the state psi of t. So psi of t is equal to e t psi, and so the derivative of this is equal to derivative of psi of t. You can resolving this, and it's better to put here the imaginary unitary, and so I for the derivative is equal to this. Perfect. So this is the Schrödinger equation. Schrödinger equation. Now, for me, it's more easy to see together two different topics to understand the topic, the bigger topic. Okay, so now I do I write this. We have the Heisenberg equation versus the Schrödinger equation. Okay, so this is the so now we have the Heisenberg equation that in Heisenberg picture that explain how does a dependent time operator work, and we have in another part the Schrödinger picture that explains how does the state dependent the time dependent states work. Okay, so the Schrödinger equation and the Heisenberg equation. These are equation of motion, because in quantum mechanics we can't describe the motion of a particle with a Lagrangian formalism or an Hamiltonian formalism. Why? Because in this video is too brief to introduce in in one's time the whole concepts in quantum mechanics. All concepts in quantum mechanics, but there are many other topics, for example, the uncertainty principles of Einstein and so on. Anyway, in quantum mechanics, I can't apply, sorry, the Lagrangian formalism. And so these are the equation of motion because describes how the expectation values variation with respect to time, the variation with respect to time of the state, the time dependent state, and the time dependent operator. Now the relationship between the state of Schrödinger and the state of Heisenberg is this. The state of Schrödinger, psi s, is equal to E h t for psi h, okay? While A of t h is equal to A of 0 s. Okay? Perfect. Perfect. Now we can talk about oh sorry, I run here has h, sorry. Okay, so now here we have this not dependent by time, sorry, I'm wrong, as, okay. Okay, now we can talk about wave function. Because if I ask you what is the wave function, you don't know how to answer. But it's normal because I don't introduce this concept called wave function. So what is a wave function? Wave function, the fourth topic in this video. So wave function. Wave function. The wave function, perfect. Okay, so we have the state psi as equal to integral in the x of psi of x for x, where x is a particular operator called position operator. In fact, we have x for state x is equal to x for x, where x is eigenvalue of the operator, and we have x for another position operator is the delta. Okay, and the same for p for q. This is delta of p minus q. Okay, now so this we have this. So psi of x is equal to x for psi. Now this is the wave function. So the wave function is the component of psi in the basis x for this Hilbert space, and this is the probability amplitude too. So the wave function is very important because it explains the probability amplitude. Very, very important. This is wave function. Now the norm is integral in the x of psi for psi, and so does is integral in the x of psi of x squared. Okay, perfect. Sorry, we have this. We can write in this way. Okay, sorry, I'm wrong in this way, because we can write this like this, and then we write the bra vector. Psi p Cp is equal to integral in the P of psi, psi is equal to this. Okay, perfect, perfect. This is always the wave function. What about operators? Operators, we have x for psi. Okay, so the operator x that h over the wave function psi of x. This is equal to x, so the eigenvalue for psi of x. So the simple multiplication, okay? Okay. Now there are many topics, but it isn't the time to talk about this. Now I have to talk. I want to talk about these important relationships. We have that P for P is equal to P for P. Okay. And then x 1 of square root of 2 pi of a of e to I pi x, and P for x is equal to minus 1 of square root of 2 pi for e to minus I pi x. Okay, now we have the wave function of p, this, and we can write that like psi of pi is equal to pi for psi, and this is equal to integral of the x for p x psi. No? Yeah, because x for psi, x for x is equal to 1. So this p for x is equal to 1 of square root of 2 pi for e to minus I pi x px. So we have integral in the x in the x on square root of 2 pi for e minus 2 e pi x of psi x. So we have that the wave function psi of p is the Fourier transform of the wave function psi of x, and this is very important. Okay, now let's talk about the last topic in this lesson, the harmonic oscillator. So the harmonic oscillator we have a particular Hamiltonian operator for this system, okay, and it's h is equal to pi square on 2m, and this is the part of kinetic energy, okay, so it's equal to ever classical quantum dynamics system plus a function u of x, and this u of x is a potential energy, okay, is a potential, and so we have that in the case of the harmonic oscillator 1 of 2 m omega square for x square, where x square is the position operator, and omega is the pulsation of the process. Now, so how to write the Schrödinger equation? The Schrödinger equation is H for psi is equal to energy for psi. Okay, and so there's p square. P square is minus 1 of 2 and second derivative. Sorry, we have for psi of x plus 1 of 2 omega square x square psi of x is equal to energy for psi of x. Okay? Okay, this is the Schrödinger equation for an harmonic oscillator. Now we can resolve this in two ways. The first way is using the Hermite polynomial, and the second way is using the creation and annihilation operators. And the second way for me is the best because these operators make us understand what the physical sense of an harmonic oscillator. In fact, this harmonic oscillator in an harmonic oscillator we have an oscillation between different states with different energy. For example, we have a state with energy econ n and econ n prime, and we can so go up and go down, energy n minus 1, so energy n plus 1, and creation of and annihilation operators creates and decreases by one particle of energy. Okay, and so we can resolve harmonic oscillator with Hermite polynomial, but and with the creation of annihilation operators. But I stop now. Okay, this is the lesson about quantum mechanics, but the people can't study quantum mechanics on this lesson because they already know something about this. Okay, okay, and in the next lesson we are going to talk about special relativity and groups theory, and from the third lesson we talk about Klein-Gordon equation and field theory and we will see again this problem, okay, with creation and annihilation operators. But now it arrived at end, so this is the end, and so bye bye, my friends, bye bye.